Hi everyone, this is Professor Majumdar and you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started. Hello viewers, today I'm going to show a two-dimensional heat transfer analysis using ANSYS mechanical APDL. It is a L-shaped body and we'll be applying different types of boundary conditions over that surfaces, right? Let us see the statement of the problem. Consider 2D heat flow over a L-shaped body. The thermal conductivity in both directions is same and it is 45 watt per meter degree centigrade. The bottom is maintained a constant temperature of 110 degrees centigrade and convection heat transfer has taken place on the top surface where the ambient air temperature is 20 degrees centigrade and the convection heat transfer coefficient is 55 watt per meter square degree centigrade. The right end is insulated, the left end is subjected to uniform heat flux of 8000 watt per meter square. Heat is generated at a rate of 5 into 10 to the 6 watt per meter cube. Obtain the temperature distribution. Okay, let us see the drawing of this one. This is the L-shaped body and the total length of this body equal to 0.06 meter and height you can see it is actually 0.03 meter, and we need to find out the temperature distribution over the L-shaped body, right? So without wasting time, let us start our analysis using ANSYS mechanical APDL, right? Let us close it. First of all, we need to create a directory and in that directory we need to save everything. Next to that, we need to change the title and let us make the title as FEA 14. Okay. Now to see the title, we can click plot replot. It will show the title at the lower left corner. It is visible right now. Okay, next to that we need to select what type of analysis it is. That will be coming from preferences. It is definitely thermal analysis. Okay, now we need to provide elemental properties and that will come from preprocessor. Element type, add, edit, delete. We need to add it and we are considering solid quad 4 node 55. Okay, let us close it. Next to that, we need to provide material properties, material models, thermal conductivity, isotropic. And you can see in this case we are having a single material and thermal conductivity of this material is 45 watt per meter degree centigrade. 45 watt per meter degree centigrade. Okay, let us close it. Next to that, we need to start modeling. Let us create areas and it will be rectangle by 2 corners. Let us see the drawing again. Let us provide the first rectangle as length will be along x direction, length will be 0.03 meter and height will be again 0.03 meter. It will be a square, right? Let us provide the first square of 0.03 by 0.03. Width is 0.03 and height is also same 0.03 meter. Apply. First one is made. Now let us see the second one again. Second one we need to provide another rectangle of length 0.03 meter and height will be 0.015 and that to be started from this location at a distance of 0.03 from x, right? So from x at a distance of 0.03 meter, we need to provide another rectangle. Width will be 0.03 and height will be 0.015. Okay, done. Now these two different areas to be joined together. That can be done from operate, booleans. You can glue these different areas together. So select first area and second area. Okay, done. These areas are glued together, right? Next to that, we need to start meshing. And here in this case we need not bother about mesh attributes because we are having single material, right? Now we can start meshing. Size controls, manual size, pick all areas. Let us provide elemental edge length as 0.0075. Okay, done. So let us mesh it. Mesh areas, free areas, pick all. Meshing is done. Next to that, we need to apply wall loading, and that will be started from here itself. First of all, we need to select type of analysis. It is a new analysis and we are considering steady state analysis. Next to that, we need to define our loads, that means the boundary conditions to be applied. Right, now load to be applied. First load will be convection at the top surface. Convective heat transfer coefficient is 55 watt per meter square degree centigrade at a temperature of 20 degrees centigrade. Right, so thermal convection on lines. Let us select these lines. 3 lines selected. Okay, so convective heat transfer coefficient, it will be 55 watt per meter square degree centigrade at a temperature of 20 degrees centigrade. Okay, done. From bottom side, we need to provide a constant temperature of 110 degrees centigrade. So define loads, apply thermal temperature on lines. Let us select bottom line, and it will be having a temperature of 110 degrees centigrade. Okay, so temperature will be 110 degrees centigrade. From left hand side, we need to provide a constant heat flux of 8000 watt per meter square. So define loads, apply heat flux on lines. From left hand side, it will be okay, and constant heat flux will be 8000 watt per meter square. Okay, done. Now another thing is there, that means from right hand side, another boundary condition is needed. The last boundary condition, heat generation rate to be provided from that body at a rate of 5 into 10 to the 6 watt per meter cube. Right, so last boundary condition, let us apply thermal heat generation on areas. Let us select all the areas. Okay, and it will be 5E6. Okay, done. All the boundary conditions are applied. Now we can run it. That can be started from solution, solve current LS. If everything is right, it will show solution is done. Okay, it is showing solution is done. So our everything is perfect. We can see our results from general post processing. Right, let us close it, and we will see results from general post processing. Plot results, contour plot, nodal solution, and nodal temperature. It will show temperature at different locations. You can see maximum temperature is occurring at the top left hand side. It is having temperature of 155.148 degrees centigrade, and minimum temperature at the bottom side. Right, you can see that is equal to 110 degrees centigrade, which one we maintained a constant temperature of 110. Right, now we'll see list results also. So list results, nodal solution, nodal temperature. Okay, it will show temperature at different locations. Right, maximum temperature of 155.15 degrees centigrade at node number 22. You can look at that node number also. Right, let us see the node where the temperature is maximum. You can remember the node is 22. Right, so what we'll do is we can plot nodes, and we can number that one also. Again, plot controls, numbering, and node number, let us make it on. So 22 is this one. So at this location, temperature is maximum. Right, okay, let us see the element again. Plot elements. Next to that, we need to see the animation of this one. So plot controls, animate, deform results. With the default setup, we want to see temperature distribution. Okay, let us see forward direction temperature distribution only. You can see how temperature is distributed throughout the body. So actually heat is coming from top to bottom, and maximum temperature is obtained at node number 22. Okay, let's close it. So this is all about our today's video. This is a very simple thermal analysis of L-shaped object. In this case, we have applied different types of boundary conditions, right? And we found the temperature distribution throughout the body. Okay, so with this one, we'll conclude our today's video. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.